Rainfall runoff relation. First of all, what is rainfall? Rain is a major component of the water cycle and is responsible for depositing most of the fresh water on the earth. It also provides water for hydroelectric power plants, crop irrigation, and suitable conditions for many types of ecosystem. The term precipitation is also used to refer rainfall. Precipitation is the natural process of conversion of atmospheric water vapor into water. Rainfall is a measurement of how much water falls as rain in a certain period of time, for example, a week or a month. Rainfall is measured by collecting rainwater across different areas and times as the amounts may differ between location and times. Now, aside from rainfall, we have runoff. What is runoff? Runoff is a precipitation that does not soak into soil but instead moves on the Earth's surface towards streams. Surface runoff, which is also known as overland flow, is the unconfined flow of water over the ground surface in contrast to channel runoff or stream flow. Runoff also occurs when there is an excessive precipitation and the ground is saturated, which means the ground cannot absorb any more water. Rivers and lakes are a result of runoff. There is some evaporation from runoff into the atmosphere, but for most part water in rivers and lakes return to the ocean. Now let's move on to the rainfall runoff relation. The rainfall runoff relationships for any rainstorm depends on the dynamic interaction between rain intensity, soil infiltration, and surface storage. Runoff occurs whenever rain intensity exceeds the infiltration capacity of the soil, providing there are no physical obstructions to surface flow. Now, why is rain runoff relation necessary? The rainfall runoff relationship can be used to anticipate runoff rate and depth. Forecasted runoff can be utilized in hydrologic and hydraulic engineering design, water availability, water supply, flood control, drainage, power production, and water resource planning and management. For the second topic, it is the hydrograph and the hydrograph separation. First, let's define what is a hydrograph. It is a graph showing the rate of flow versus time past a specific point in a river or other channel or conduit carrying flow. It is also referred to a graph showing the volume of water reaching a particular outfall. It is used in the design of sewerage, more specifically the design of surface water, sewerage system, and combined sewers. Now here are the factors influencing a hydrograph. For a watershed characteristics, the factors are size, shape, slope, storage. As for the hydrograph with infiltration characteristics, it involves soil, land use, and cover. As for climatic factors, it involves rainfall intensity and pattern, areal distribution, duration, or the type rainfall versus snowmelt. Now, uh, a unit hydrograph is converted to a hydrograph by multiplying the coordinates by the runoff value or effective rainfall exposed in centimeters. The maximum ordinate of the unit hydrograph can be multiplied by either the effective rainfall expressed in centimeter or the runoff value expressed in centimeter to determine the peak flow resulting from a storm of the same unit period. It should be noted that rainstorms don't necessarily last the same amount of time. The unit hydrograph theory allows superposition in these circumstances. It is feasible to split a longer lasting storm into two or more shorter lasting storms for which a unit hydrograph is provided. The total hydrograph can be obtained by drawing the true hydrographs with the appropriate lag time but overlapping each other as if they were two independent hydrographs. The figure shown is an example. Now, let's go to the components of a hydrograph. First component is a rising limb, also known as a concentration curve, reflects a prolonged increase in discharge from a catchment area typically in response to a rainfall event. Now the second one is the recession. Extends from the peak flow rate onward the end of storm flow and, and the return to groundwater. Derived flow is taken as the point of inflection of the recession limb. The recession limb represents the withdrawal of water from the storage built up in the basin during the earlier phases of the hydrograph. The third one is the peak discharge, the highest point on the hydrograph when the rate of the discharge is greatest. Now, the fourth one is discharge. Discharge is the rate of flow, volume per unit time, passing a specific location in a river or other channel. Lag time. This is the time interval from the center of mass of rainfall excess to the peak of the resulting hydrograph. Time to peak. This refers to the time interval from the start of the resulting hydrograph. Now, let's move on to the hydrograph separation. Hydrograph separation refers to a various analyses that are commonly performed to decompose hydrographs into sub-hydrographs. It is important to recognize that hydrograph separation are performed to answer two distinct questions. The first question is, what is the volume of water that was added to the stream? The second one, what is the source of water that was added to the stream? Hydrograph separation is considered as the first step to catchment scale water balance analysis. A wide variety of hydrograph separation methods exist ranging from empirical to analytical and physical. Another information, hydrographs are also separated into event flow, sometimes called quick flow, and base flow, which is sometimes called delayed flow, in order to understand the magnitude of the hydrologic response. The separation of event flow from base flow can be done by relatively simply graphical means. Methods to determine that endpoint are approximation subject to users' decisions. These analyses can be used to calculate runoff ratios and the timing of the hydrologic response. Hydrograph separations are separated. Hydrographs are separated to determine the origin of water that arrive in the stream. A simple conceptual model is that event flow is a mixture of water that was added to the watershed during the event and snowmelt called new water, and water that existed in the watershed prior to the event, which is the groundwater and soil moisture, are called old water. It is important to recognize the event flow can be a mixture of new water and an old water. Water added to a watershed during a rain or snowmelt event is not necessarily the same water that appears in the resulting stream flow event.
So the topic that I'll be discussing is unit hydrograph. So first things first, we need to identify what is unit hydrograph. So a unit hydrograph shows a temporal change in flow or distance per unit or runoff. So in other terms, it is how the flow of a stream will affect over time the addition of 1 unit of runoff. So unit hydrograph is a very useful tool in the process of predicting the impact of precipitation on the unit flow. It is just a hypothetical unit of a watershed in terms of runoff volume and timing to a input of rainfall. Hydrograph, which result in 1 inch excess rainfall. It is always 1 inch excess rainfall and its volume is 1 unit inch. Yung high unit hydrograph also is specified as being 1 hour, 6 hour, or 24 hours unit hydrograph, etc. So what is the purpose of unit hydrograph? It is used to transform excess precipitation into design storm hydrograph. So hydrograph is just answering how will runoff affect the flow over time. This is the graph of a unit hydrograph theory. So the rising climb is a part of the hydrograph between where it begins to rise and the peak flow. The recession limb or recession curve is the part of the hydrograph between the peak flow where the flow returns to respectively steady state. The inflection point is the point on the recession curve of the hydrograph where the slope of the graph becomes less steep. So this indicates where the base flow becomes more important to the total flow than the quick response runoff. This is the important terms in unit hydrograph theory. So the time to peak, which is sometimes called lag time, is the time where the midpoint of the precipitation period to the peak flow. Also, the time of concentration is the time from the end of the precipitation period to the end of the quick response runoff in the hydrograph. This represents runoff traveling from the most remote location within the watershed. So here is this example of calculating the unit hydrograph. In the given, assume the total runoff hydrograph was measured over 4 hours in 30 minutes interval. The catchment area is 100 acres. Base flow is equal to 10 cubic feet per second and the total hydrograph QT is equal to 50, 80, 160, 210, 180, 155, 110, and 60 cubic feet per second. So let's determine the unit hydrograph. First things first, we need to get the direct runoff hydrograph. So to get the direct runoff hydrograph, let minus the flood hydrograph to base flow. So we have the given of base flow 10 cubic feet per second, and then we have the given of flood hydrograph or the total hydrograph. So 50 minus 10 we have 40, 80 minus 10 we have 70, 160 minus 10 we have 150, and so on. After calculating the direct runoff hydrograph, we're gonna get the runoff depth, which the formula for runoff depth is a volume of DRH or direct runoff hydrograph over catchment area. First, we have to get the volume of direct runoff hydrograph. So to get the volume, the total volume of water from the quick response runoff need to be calculated. This is done by summing the area under the quick response runoff hydrograph for each time step. In this case, it is hourly. So we have the volume of DRH is equal to the summation of DRH. So the volume of DRH from the given above, we have 40, 70, 150, 200, 170, 145, 150. We're gonna just sum all it up and times it to 30 minutes times 60 seconds for conversion of minutes to seconds. So we have now the volume of DRH is equal to 1,665,000 cubic feet. And since we have the catchment area given, 100 acres, we're just gonna convert it to cubic feet. So 100 acre is equal to 43,560 cubic feet. So we are now have the catchment area 1,356,000 cubic feet. So since we have the volume of DRH and catchment area, we're just gonna plot it to the formula and multiply it into 12 inches because for the conversion of feet to inches. So we have now the runoff depth of 4.5864 inches. After getting the runoff depth, calculate the unit hydrograph. So the formula for unit hydrograph is equal to direct runoff hydrograph over runoff depth. So since in the given we have the direct runoff hydrograph, so in the given, since we have values of the direct runoff hydrograph and runoff depth, we're just gonna plot it to the formulas. So we now have a unit hydrograph is equal to 40 over 4.5864, 70 over 4.5864, 150 over 4.5864, and so on. And then after we're gonna simplify it into simplest form. So the we now have the unit hydrograph of 8.7, 15.22, 32.61, 43.48, 36.96, 31.52, 21.74, and 10.87 CFS per inches. And that's how you get the unit hydrograph. Thank you.
Estimation of discharge using unit hydrograph. What is unit hydrograph? A discharge hydrograph produced by one unit of uniformly distributed net precipitation over a watershed. Estimation of discharge using unit hydrograph. It is now understood that a unit hydrograph is a type of unit used to measure runoff resulting from a specified or unit period of rainfall. According to a unit hydrograph, 1 centimeter of direct runoff naturally results from 1 centimeter of useful rainfall. Therefore, the ordinates of the direct runoff hydrograph will be twice as large with the total runoff period being the same if the effective rainfall in the same duration is double or 2 centimeter, just like shown in the figure 4.10. Peck flow by unit hydrograph method. Here is the sample problem. Here are the coordinates for a 6-hour unit hydrograph for a 1,000 kilometer catchment region. This is the table for the sample problem. 18 hours passed during the storm. For 6-hour intervals, the effective rainfall increments or rainfall excess are 0.6 cm, 2 cm, and 1 cm respectively. Calculate the hydrograph for runoff. Find out the runoff volume as well as the peak flow. One may assume a 100 cubic base flow solution. As indicated in the picture above, the computation can be performed in a tabular format. The maximal ordinate flow is 664 cubic, which is the peak flow. It can be found by graphing the base flow and 3 hydrographs with a lag of 6 hours each. The 3 hydrographs ordinates are derived from columns 4, 5, and 6.
Rational method. The rational method expresses a relationship between rainfall intensity and catchment area as independent variable and the peak flood discharge resulting from the rainfall as the dependent variable. This another process in hydrology cycle. This one of the simplified method pero marami siyang limitation. Runoff is yung water na nag-flow sa surface which is kaya nating ma-measure sa outlet. Kasi lahat ng runoff naman eventually pupunta naman siya sa outlet that make us possibly measure it. Makukuha natin ang actual runoff ng ulan dito sa outlet since bawas na lahat ng na-infiltrate or na-evaporate. It has been used for over 150 years and known as the rational method for nearly 100 years. It is widely used in the design of storm water drainage system, farm, dams, spillways, and small culverts in road and railway embankments. Here's the rational method. Q equals to CFCIA, where Q is the peak flow, CF runoff coefficient adjustment factor, C runoff coefficient, I rainfall intensity, A drainage area. But mostly, hindi naman na naggamit itong CF. Anyways, dito, this table is our reference for RC. RC is based on what land use we are conducting. We have pavement and roads, earth, shoulders, drive-on walls, and etc. And we also considering a flat, rolling, or hilly area. However, when we are going to measure more than one type of area or area is not uniform, we are going to use this formula. C, or the C composite, is equal to summation of CI AI over area total. Adjustment factor, ito naman yung reference sa CF. Yung CF, depende naman siya sa recurrence interval or the recurrence period. 10 years, 25 years, 50 years, and 100 years. Tsaka yung sa other side naman, yung adjustment factor, which is 1.0 sa 10 years, 1.1 sa 25, 1.2 sa 50, and 1.25 sa 100 years. Kaya sabi ko kanina, mostly di na ginagamit yung CF kasi mapapasin nyo yung 10 years is equals to 1, which is imo-multiply naman siya, so mawawala din naman. Itong recurrence interval, ito yung binibigay natin na classification sa ulan, depende sa probability niyang mangyari. Palaki ng palaki yung recurrence interval mo, palit ng palit naman yung chance niya na mangyari taon-taon. Time of concentration is the time required for an entire watershed to contribute to runoff at the point of interest for hydraulic design. This time is calculated as the time for runoff to flow from the mostly hydrologically remote point of the drainage area to the point under investigation. Pag di mo nakuha yung average or uniform rainfall intensity, we use time of concentration. Ito yung time for water travels mula sa farthest point to the outlet. But to clarify, hindi lang yung farthest flow path yung i-compute. Lahat ng flow path na connected sa outlet, i-add siya lahat. Tapos, i-base naman siya dito sa RIDF na curve. Assumption and limitation applies to small urban watersheds with drainage area not larger than 200 or 80.94 hectares. So, yun na. Dapat maliit na watershed. And urban, malapit sa city. Kasi dapat na ina-apply sa mga impervious na areas. Or yun nga yung mga nasa concrete. Kasi yung assumption ng rational method, lahat ng ulan magiging runoff. So, parang hindi as in na-consider yung mga na-infiltrate and the other.
The peak flow is assumed to occur when the entire watershed is contributing runoff. The rainfall intensity is assumed to be uniform over a time duration. The peak flow recurrence interval, in other words, the 10-year rainfall intensity is assumed to produce the 10-year flood. So, we have a sample problem. A small urban watershed has an area of 70 hectares and is generally composed of light industrial areas. Calculate the peak runoff equivalent to a 25-year return period as its outlet if the observed rainfall intensity is 5 mm per hour. So, di na tayo magko-compute ng time concentration since nandito na yung rainfall intensity. Equation natin, Q equals CFCIA, we have A, 70, we have I, 5 mm per hour. C natin, light industrial, we will use flat, 0.50. CF, 25 years, equals to 1.1. I-multiply lang natin lahat. Then, we will get Q equals to 107 cubic meter per second.
Now let us discuss the SCS-CN curve method. The SCS runoff curve number method is developed by the United States Department of Agriculture or USDA Soil Conservation Services and it is a method of estimating rainfall excess from rainfall. The SES curve number method is a simply widely used and efficient method for determining the approximate amount of runoff from a rainfall even in a particular area. Although the method is designed for a single storm event, it can be scaled to find average annual runoff values. The stat requirements for this method are very low: rainfall amount and curve number. The curve number is based on the area's hydrologic soil group, land use, treatment, and hydrologic condition. The basis of the curve number method is the empirical relationship between the retention or the rainfall not converted into runoff and runoff properties of the watershed and the rainfall mucus found in equation 1, appropriate to describe the curves of the field measured runoff and rainfall values, where in equation 1 it is F over S is equals to Q over phi, where you can get the phi by simply subtracting the value of Q to the value of P, where F equals to P minus Q, or the actual retention after the runoff begins. Q stands for the actual runoff, while S stands for potential maximum retention after the runoff begins, where the symbol phi is the potential maximum runoff. The three important abstractions for any single storm event and are rainfall interception, meteorological rainfalls minus true falls, stream flow and water drip, depression storage, and infiltration into the soil. The curve number method lumps all three abstractions into one term, the initial abstraction, and subtract that is calculated value from the rainfall total volume. The total rainfall must exceed this initial abstraction before any runoff is generated. This gives a potential maximum runoff or rainfall available for runoff as P minus IA. As for the equation 2, P minus IA minus Q all over S is equals to the Q over P minus IA. It is important to note that the potential maximum retention term S excludes IA. Hence, for a given storm, maximum loss of rainfall is S plus LA. Remaining terms in equation 2 for Q gives. So to find the value of Q is P minus IA squared all over P minus IA squared plus S. Establishing the relation to estimate it was LA was challenging. The SCS provide the following empirical equation for based on the assumption that LA was a function of the potential maximum retention or S. LA is equals to IA is equals to 0.2 seconds. 0.2 S, not seconds, sorry. The potential maximum retention S is related to the dimensionless parameter Cn in the range of 0 greater than or equal to Cn or greater than or equal to 100 by equation 5. So to get the value of S is equals to 1000 all over Cn minus 10. Now substituting equation 4 into equation 3 yields Q is equals to P minus 0.2 S squared over P plus 0.S squared S. Equation 6 has only one parameter that needs to be evaluated, which can be determined by using equation 5 and curve number tables published by the SES. The solution of the SES runoff equation is shown below. Curves on the sheet are for the case 1 is equal to 0.2s, so that Q is equal to P minus 0.2s squared over V plus 0.8s. When the drainage area consists of land use with the impervious cover, TR-55 provides separate graphs for computing the composite curve numbers values depending on the percent of the impervious cover. However, it is a good practice to calculate the runoff from impervious area and pervious area separately and then add the volume. That would be all. Thank you.